let me mention that 35 years ago, we started a whole series of analyses from codes that we took from Venus and how Venus changes in a runaway greenhouse to the Earth. And we modeled what happens at Earth if we had a little CO2. And 35 years ago, that was the start of how we now understand about climate change. What's happening on Mars today is we're now in the realm of the supercomputers to really delve in and understand its atmosphere through developing global circulation models, through developing new concepts of how to tweak the environment and what changes that produces. And there's nothing like having human presence on Mars. As you know, humans are terraforming the heck out of this planet. And so there's processes that will begin as humans begin to live and work on the red planet. Well, we know an enormous. So what have we learned about Mars? I want to talk about, before we can really talk about what kind of changes will occur when humans show up on the red planet, we really got to understand what the baseline is. Well, over the space program, we've learned an enormous amount about how Mars has changed over time. So early on, 3 billion years ago, Mars was a blue planet. It went through rapid climate change, about 2.5 billion years, and it now is the arid and very cold planet we see today. We have a lot of ground truth, we call it, with a lot of our missions. This is a Mercator projection of Mars, for which the blue areas are the lowlands, the high areas are the reds and the whites. The green areas are the ancient shoreline of Mars. So when we go and look for life or signs of life, these are where you'll see many of our missions. The Phoenix mission, however, in the high altitude, latitudes rather, dug into the dirt looking for where water might reside on the planet. And it found it just below the surface. The concept is some sort of water layer then would be, as you go towards the equator, deeper into the planet. Okay, deeper into the planet. We now know the crust of Mars doesn't produce plate tectonics. So it is what we call a stagnant lid. And Mars, we're finding out with insight, is actually quite hot on the inside. So that means it has magma, it has volatiles, it's being trapped by this stagnant lid, and there's a water layer there. So there's a significant amount of water in the crust of Mars. The solar winds stripped a lot of the atmosphere and a lot of the water away from Mars, but indeed we believe there's a frost layer well into the soils. And of course, we're tasting that with curiosity. The atmosphere, of course, is dominated by CO2, but there are trace gases. Nitrogen is very important, oxygen, argon, and carbon monoxide. The temperature variation is enormous. 170 degrees Fahrenheit variation in one day. And indeed, this is what has locked in a lot of that water in the crust of Mars. Pressure-wise, here's two seasonal looks at how the pressure changes on Mars, one during the summer, one during the winter. And what we see is everyday solar heating heats up the ground, and a pressure wave of CO2 goes through the planet, particularly during northern hemisphere winter, as the sublimation of the CO2 in the southern hemisphere occurs. There's no polar cap then, and that CO2 ends up into the atmosphere. The key diagram here is on the right. This is a phase diagram for water. You can see where Earth is, where you have a pressure and temperature, and that whole triangle that says liquid. This is where water would exist on the surface. And of course, it exists on the surface of Earth. But as you can see, Mars is virtually at the triple point. We've got to raise the pressure. We've got to raise the temperature to get it to the point where liquid water can be maintained on its surface. Once we start doing that, then a whole series of other changes can take place. Well, if this is the current status of Mars, how did it get that way? Well, Mars lost its magnetic field. It had one, a significant one, probably at least 3.5, maybe 4 billion years ago. And so the solar wind has been stripping the atmosphere of Mars. And MAVEN has been measuring an average of 1.3 kilograms per second is being stripped. Now, conceptually, today, Mars' atmosphere is in equilibrium with the solar wind. That means what it strips is being outgassed, and that's how come we have an average of about 7 millibar per year of pressure on Mars. Conceptually, if we can stop the stripping, Mars will then increase in pressure, and the increase in pressure will mean an increase in temperature. Unfortunately, many heliophysicists believe that Mars's low pressure is really due to stripping from extreme solar wind events. So these are huge coronal mass ejections that hammer the planet, ripping huge pieces of the atmosphere away. And we're now realizing that the sun does this. Here on Earth, the first really big event we call the Carrington event here on Earth. It happened in 1859, where aurora, this was such a huge event, the aurora is an indication of how the Earth's magnetosphere is rearranging and protecting itself against the solar wind, goes through Canada, through the United States, through Mexico, through Central America, and if you were in Colombia and looked up, you would see an aurora. That's right. This was an enormous event. It produces currents in the ionosphere, which then disrupt electrical equipment on the ground. This is why we are very concerned about our power grids, how they can be affected by these solar superstorms. So what we've done is, what does the solar superstorm look like on Mars? So once again, we go in our supercomputers. We really do the analysis. So the pre-storm events, you can see is a very low current that's generated. Mars in itself is the red circle. So instead of the ground being a sink of current, the ground becomes a source of current. And it's an induced current that comes from huge currents that arise in the ionosphere. And the peak storm event is shown on the right-hand side, which is twice a Carrington event. So we must be able to learn, if we're going to live and work on this planet, that we'll have superstorms sometime in its future, and we have to be able to fend against it and come up with a strategy. So not only are electrical equipment susceptible, but also the atmospheric pressure as it begins to strip the atmosphere away. Well, we all know that Mars's atmosphere is thin. Therefore, cosmic rays have an opportunity to make it to the surface. And as you can see in this particular diagram, altitude versus energy deposited by a whole series of energies of cosmic rays. Mars's pressure is such that we have many significant high energy particles making it to the surface. So a thicker atmosphere would help. That would then lower that curve, just like it is done here on Earth. But also a magnetic field would also enhance that activity in terms of lowering this ionizing radiation, making it to the surface. So let me mention now, that is the baseline of what we know. Now let's go back into supercomputers and figure out what can we do to be able to mitigate a number of these problems. And let's start with the human exploration zone. Unlike the movie The Martian, where NASA established a number of bases every time it went there, the current plan is that we will go live and work in one area called the exploration zone for all our missions into the foreseeable future. So this exploration zone is about 200 kilometers in diameter. We land in one area, we live in one area, and we also want to use the resources that are there through ISRU activities. We want this area to be scientifically rich. And so there's been a fair amount of discussion as to where this area might be on Mars. We've already had a workshop and have identified about 45 different sites. And over the next couple of years, we'll have another workshop and narrow that down even further. So conceptually, how do we protect this first foray to Mars, for which we want to be on the planet for long periods of time? Some believe forever. If you land, you stay, right? So one of the ideas, of course, is let's protect it with a magnetic field. The first concept we investigated, once again in supercomputers, this is where we're at right now, is generating a magnetic field at Mars L1. This is the Lagrangian point. Lagrangian points are very specific areas in space for which it is always in front of you and the sun and orbits with you. It's a very unusual spot, and it's due to gravitational pulls and tugs by the sun and the Earth canceling out, allowing you to then follow the Earth. So what kind of field do we need that would mitigate a number of these things? Because the magnetosphere can generate a huge magnetic field at this location, we can actually situate Mars in the magnetotail of this huge current system. Well, how do we generate a magnetosphere? Well, here on Earth, we basically have what we call the base field is called a dipole. This is like a bar magnet on the left, where the magnetic field originates in the interior, and then the field moves out in these large circles. But in a similar way, you can create, through a current loop, a dipole-like magnetic field. And so there's actually some work being done on generating large magnetic fields at Rutherford Appleton Laboratory. They're building tokamaks, and they need confinement. They use very large magnetic fields. And so conceptually, they are using these kind of currents, these current loops, to generate a dipole-like magnetic field. And to generate something about the Earth's intensity of the Earth's magnetic field, you need a total power of about 65 gigawatts. There's also work being done with plasma terminals, where you can create, once again, a current loop, and then the plasma is moved from one terminal to another, accelerated as you go along, generating a large magnetic field. And this requires fusion reactors to be able to generate the power necessary to do these. Okay, so let's say we can generate fields, maybe as large as these, well into the future. How would we apply them in this particular case? Well, the first example I mentioned would be generating a dipole-like field through these current systems at Mars L1. And this is a full-blown, three-dimensional MHD simulation that shows that we have Mars in the center of the magnetotail. And here's the solar wind being diverted around, which contributes, of course, to the interaction with Mars without a magnetic field, and produces the stripping. The pressure is also an incredibly important element of this, and you can see Mars is really well protected, not completely protected, but relatively well protected. So these hybrid simulations show that the stripping is stopped by about 2 orders of magnitude. Now, this is really quite exciting. It has a number of advantages. And as I mentioned, if you stop the stripping, the outgassing is going to continue. And as the outgassing continues, the pressure goes up and the temperature goes up because of that relationship, and you establish a new equilibrium. It's the beginning of Mars terraforming itself, if you will, literally changing globally the environment. Now, probably the best set of simulations we've done, since the previous one requires a huge magnetic field to be able to produce this, on the order of the size of the Earth's magnetic field. Okay, so 65 gigawatts of power will have to be generated in that environment. But can we come closer? Can we produce another magnetosphere that has the same effects closer to Mars, that has more benefits? And it turns out we can. And what we do is we create 4 current loops at aerostationary orbit at 4 locations around the planet. And when we do the computer analysis of this, we see the noon midnight projection on the left. You can see the 2 currents in this plane, one on the night side, one on the day side. You see how Mars is bathed in those magnetic fields and therefore well protected, not only from the solar wind, which comes from the left, hitting this artificial magnetosphere, but literally, in this case, nearly prevents the stripping. It's now 3 or 4 orders of magnitude less stripping that goes on in this particular case. And this is with all the currents in the current loops moving in the same direction. And the right-hand rule tells us those are North Pole current systems. If we look down on this system, in other words, cut it in the equatorial plane, we see how these 4 current systems literally bathe the surface of Mars. Okay, so we stop the stripping. Also, this is, we believe, the best protection against a solar superstorm from stripping the atmosphere. And then, of course, you have the larger magnetic field intensity helping you reduce the cosmic radiation that gets to the surface. Now, here's another example where we've changed the direction of one of the dipoles such that it's a southward seeking one, and that's the one on the left, sorry, the one on the right. The one on the left has both the current systems moving in the same direction, and we call those North Pole systems, dipole aligned systems. And the one on the right has a north and a south pole. The one on the right literally stops the stripping. Now, Mars's atmosphere, just like the Earth's, is going to heat up based on solar radiation. And as soon as it heats up with solar radiation, what happens is the ionosphere expands into space. And when it does, here at Earth, it's trapped on our magnetic field lines. And we call that region around the Earth where the ionosphere is literally evaporated into space, but trapped, the plasmasphere. And in both of these cases, we have a trapped plasmasphere where material moves down into these field lines and then is trapped. Now, what that means is as soon as these field lines fill up with ionospheric plasma, they stop the evaporation. Yeah, thank you. I pulled a muscle in my back yesterday, and it's doesn't help me. Sorry. Thank you very much. So this helps maintain as much of the atmosphere as you possibly can while Mars continues to outgas. Once again, the interior of Mars is hot. Insight's even found that the core has an outer layer of molten, will be iron and nickel although it's not generating a magnetic field. That's typically where it does. This means that Mars itself has a huge potential to continue to outgas. Now, what would it be outgassing? Well, the primary outgas is CO2. But if you heat Mars up, you'll get more of the water that's trapped in the crust. And water vapor is an even bigger greenhouse gas than CO2 is. We also know that Mars leaks methane. We don't know the origin of methane. It might have been old methane that's trapped below the ice layer. We see from Curiosity, that is, that crust heats up and becomes more porous. Methane appears to leak through the surface. And so consequently, we might also see, in addition to CO2, in addition to water vapor, more methane. Well, methane is also an enormous greenhouse gas. In fact, the ordering is water vapor, methane, CO2. This also will, we believe, continue the process of letting Mars heat up. Add more material into space in the atmosphere, you then also increase the temperature. Now, these magnetic fields can be mapped down to the surface, and when we do that, here's where all northern magnetic fields map to the surface. And of course, because they're at aerosynchronous orbit, they move with Mars on a daily basis. So you place one of these directly over the exploration zone, where you maximize the amount of magnetic energy to the surface, protecting that environment, protecting it from by lowering the cosmic ray input, by stopping the stripping as the solar wind comes by. And you end up with a surface magnetic field that looks like this. Now, if you can imagine being in the center of this diagram at 0 degrees longitude, 0 degrees latitude, and you had a compass. As you traveled in that environment, you literally can geolocate yourself, because you now have, you know, north, you know, south, based on the intensity of the field going down. You then can figure out which latitude you're going to. And so it also adds the possibilities for locating yourself on the surface. Once again, you can also change how these fields arrange based on their current systems. And here you see the central location has little magnetic field, whereas the other two areas are really intense. And so consequently, once we learn how these four dipole systems are managing the solar wind, we can change their current direction, which changes the current field, which is a dipole-like field, and literally changes that surface magnetic field that provides or aids in protecting the exploration zone. So here's another example where we've had two of them are going north and two of them are going south. Okay, so in conclusion, let me mention these kind of concepts, much like the climate change concepts that emerged 35 years ago, are in the realm of the supercomputers right now. This is what we have to do to understand what effects happen based on our knowledge of the environment, our knowledge of Mars, and how to protect human assets and their equipment and their infrastructure on the planet Mars. Thank you very much.
Hello, I've done some back of envelope calculation, and you mentioned that we are stripping the atmosphere at a rate 0.1 kilogram per second.
Yeah, low speed solar wind.
Right. That means at 1 year, we are stripping 3 million kilograms. And that means that in 1 year, if we block the stripping completely, we would increase the atmosphere by about 1/10 of a billionth basically the atmosphere of Mars is 3 × 10⁻16, and we are increasing the atmosphere by 10⁶, right, a year, which means that assuming linear progression, which would not happen, but assuming it, in 10 billion years, we would double concentration of the gases in the atmosphere. So the question for you, if we prevented the stripping of the atmosphere completely, how long would it take to increase the atmospheric pressure by 1%?
Yeah, it takes a long time.
And,
So that's
yeah,
that's
second
currently
point,
correct.
second point, if you prevent the stripping, you also prevent the accumulation of the solar wind hydrogen, which is arriving. And to point out how weak effect this is, Venus, which is much closer than Mars to the sun, does not have a magnetic field at all as well. And as you know, it has much thicker atmosphere, and the stripping is in equilibrium with the amount of hydrogen brought, and stripped is in equilibrium.
Yeah. So Venus's atmosphere is getting stripped enormously. The difference is Venus is generating a lot of it through its volcanic activity. Oh, how long does it take if that was the only process, it does take thousands of years. Yeah, thousands of years. But that's not the only reason why we do that. Yeah. Steve.
What we teach our students, which does not necessarily mean we teach it correctly, is that the reason why the atmosphere is at the triple point is because it's regulated by the alkaline basalt, which is exposed over Mars. So if you raise the atmospheric pressure more, you would get more rain, which would then erode more basalt, which would put more alkali into play, which would absorb more carbon dioxide, so that the pressure would go back down, which means it would rain less, which means and then you would restore carbon dioxide from outgassing. Is that wrong?
No, you're right. You're right. What we've started to do is use supercomputers for looking at, through the Mars Climate Modeling Center, the MCMC, what happens as we change pressure and temperature. There's a variation across the globe. What happens is the temperature increases at the equator, but decreases over the pole. So the atmospheric interaction you're talking about, we haven't completely feathered out what would happen in that area, but we have started that process. I didn't show any of the results of that. Okay.
Dr. John Brandenburg from Kepler Aerospace, and I'm a plasma physicist, so I've enjoyed your talk very much. Just wanted to ask, if the stripping models for Mars are exactly what they say, why wouldn't Venus be a barren planet like the moon? Because it's much closer to the sun and has no magnetosphere. You've partially spoken to that, but could you expand on that, please?
Yeah, Venus is much larger. It maintains a huge gravity, holds more of the atmosphere, and is far more active in volcanic systems over its lifetime. In addition to that, some of the more recent modeling seems to indicate Venus was also a blue planet, and this runaway greenhouse effect really only took over in the last 800 million years. So unlike Mars, it has a very different evolutionary track. Yeah. All right. You're very welcome. Thank you.